complexity last time, and the aim in amortized complexity is to minimize time, total worst case time. So time here is worst case time, but for a sequence of operations on a data structure. It's typically something on a data structure, and we're trying to minimize not for one operation but for a sequence of operations. And the average time, so if you do something like 3 operations, then amortized complexity of your T is very large, okay? Something sufficiently large, and so that is amortized complexity. And why is it important? Well, we saw that there are applications like maybe when you want to apply some data structure for a graph algorithm, you are not really doing one operation, you are doing a bunch of operations. And so when I say this aim, there are two aims here. One is estimation, which is that, I mean, if I care about total time for T operation, I can always find the worst case time for one operation, multiply by T. Clearly that is so. Amortized complexity is always bounded above by worst case time, because you can just simply say if this delete min operation takes log n time, then if I'm doing n such operations, at most n log n. So log n is also an upper bound, but often it may not be a good upper bound. Okay. So the example I was telling last time was that, let's say I want to find out your monthly expenses, okay, and I ask you what is the maximum you spend on any single day, and you say on 5th of the month I paid my mess fee 2,000 rupees. So that is your worst case. So I multiply by 30 and say, okay, your monthly expenses is at most 60,000 rupees, right, or 6 lakhs or whatever, 60,000 rupees, which is completely a gross overestimation, right? And the reason you spend that 2,000 is because you don't have to pay rent every day. You don't have to pay for food every day. So this is this notion of amortization, which is that an expensive operation sometimes is either preceded or succeeded by a lot of cheap operations, right? It doesn't happen all the time to say, okay, I multiply by that and give me an estimate, right? And now, so this is the notion of you want to do a tight estimation of this overall time. And it's a challenge because there is some dependency on the operations, right? So you can't just individually analyze the total time, because this operation is expensive and then that causes some other things to be cheap. So you need to capture this dependency somehow and argue. Okay, so that makes the tight estimation problem a bit harder. And the second goal is also that if my goal is to design a structure which minimizes amortized complexity, then you may want to even design different data structures, right? So one is that here is the structure, tell me what is the amortized complexity, is my estimation correct, do a tight estimation. The other is, okay, now for example, for the case of applying a heap on a shortest path problem or something like that, I don't care about worst case time, so I give you some flexibility now, design a different kind of a data structure where worst case may be bad sometimes, but overall, so this is design better data structure focusing on amortized complexity. Right, so this was 2 different goals, and you're just getting practice on how to do this computation of this estimation of amortized complexity. And there were, at least Corman's book mentions 2 or 3 ways of doing it. One is an aggregate method. Yeah?
Sir, actually the voice is not audible.
Okay.
The audio is not clear.
Okay.
The video quality is also bad.
Hello, is the audio okay?
No, sir.
No? Is this better? Hello? Is this better?
No, sir.
So is Vivek sir there? You can talk to him and see whether there is a problem there. I mean, looks okay from our end. Okay, I'm going to continue. Okay. So Carmen book calls these three ways of doing this amortized analysis. Okay, the terms don't mean anything. I'll just tell you what they are. So in the aggregate method, you want to look at again not one operation at a time, but you do a sequence of operations and somehow overall figure out how much cost it takes. Right? And which may not always be possible, but so that's and in the potential. So is the audio better? Is the audio better?
Sir, our video number please, sir.
They're freezing, yes. Okay, I'll continue because this is something they did last time. So in the potential or credit method, okay, so I'll tell you. So the two toy examples we saw, you would have seen, is this incrementing a binary counter. Where you have a B-bit counter. And you just want to do increment.
Excuse me, sir.
Yeah.
Sir, your voice is not clear. Can you be louder?
Okay.
Or can you increase the volume from there?
Here it's all full volume and both from the mic and from myself. So looks like there may be something local there. You have to check. And I'm revising what you did last time because there are some new people joining here. So in the meantime, please see whether you can work with Vivek sir to fix the things there. Okay. And I'll take a break when I'm going to start something new, so we will be on the same page. So I want to do this increment, and let's say I do some large number, some t increments. Right? What is the worst case time for an increment operation?
So the least bit will take all t increments. The second one will take t by 2.
Wait. You're jumping ahead. First of all, we're talking about b bit counters.
Okay.
Right? I'm saying, what is the worst case time for a single increment operation? Order B, because in the worst case they're all 1, 1, 1, 1, 1, and you might want to change that to C. So worst case is B is the worst case time, and if I'm doing T increments, an estimate would be overall time will be T times B. And we want to argue that actually you can do better. And why do we even think it's better? Because you don't have to increment 1, 1, you don't come across 1, 1, 1, 1 all the time, but well, maybe not all 1, 1, 1, 1, maybe you will come across B by 2 running time, right? Will that happen? How do you capture the dependency between these things? And that's where your argument of, what did you say? Yeah.
The least bit will always
Yeah.
increment.
So now we will
It will
count.
always change and
So we will count the total time for T increments in a slightly different way. Instead of doing one increment at a time, we will see the last bit and see how many times that got incremented. Well, every time that got changed,
Okay.
right? So that got flipped. So that's T. And then we see what about this bit, how many times it gets flipped. It's T by 2 times. And then the next one will be flipped T by 4 times. And T by 8 times. And if you go even all the way up to infinity, this is at most 2T. And that is the total time, not T times B, but 2T. So the amortized complexity is 2. Okay. So this is this aggregate method. Somehow you look at a big picture of the whole sequence of increments and overall somehow count it. Okay. The potential method or the credit method comes with the following thing, right? So if you just recall your monthly expense analogy, then you are given a certain amount every day. That is the amortized complexity. Now if you spend less than that, then you put the remaining in some bank account, which in our case is the data structure, which in our case is the counting, right? And if you need more for your expense, just borrow it from there. Now the trick of amortized complexity is to come up with how much do I need every day so that I never need to borrow from outside, right? Even if whenever I need a lot of money, it's there in the data structure. Okay, so the amount of credit or money in the data structure is sort of like amount of overcounting we have done, right? If the increment actually takes 1 unit of time, I'm going to count it as 2. Okay, because later on, if somebody else needs 3, I'll count it as 2 because the one overcounting I have done it here, because it's all about accounting, right? We are distributing this cost and we want to count the cost for the total number of operations. So we will do this distribution. So how much credit should I come with for each operation so that if I spend less, then I put it on the structure, and if I spend more, I borrow it from the structure, but I never need to borrow from outside. Okay, so that is, and usually this, if I manage to get this aggregate thing, it tells you an idea of how much credit I should come with, right? So I give each operation some 2 credits and say, okay, this is what I'm going to count. 2 is your allowed cash. Now if you spend less, put the remaining out there, and whenever some operation, what is the idea here? What is the intuition? That if I have an increment like this, where I'm going to spend a lot of time to do this flips, that I have done a lot of overestimates before that I can use those money to pay for this. Now, so how do I distribute this 2 units, right? So this potential method says, or where do I, okay, so there is a, so what it says, so the amortized cost for the ith operation, let's say, is the actual cost of the ith operation plus the potential in the data structure after the ith operation minus what it was. So this is a potential, something on the data structure, some function of the data structure, something which is greater than or equal to 0. This is called the then this is like a formula, and it fits with the intuition that if the actual cost is less, okay, amortized cost is the credit given to the operation. Okay, actual cost is less, then the remaining I am going to put it in the data structure, so the potential in the data structure will increase. Right? Phi of di is what is the potential after the ith operation. Since the actual cost is less than what the amortized cost is, this potential will increase phi di minus phi d minus 1. If the actual cost is more than what I am bringing, then I am going to borrow from the data structure, so potential will decrease. So this quantity will become negative. Okay? It fits the intuition, and this is something I did not do last time. How is the audio now? Is that okay? Is the audio okay?
No, sir.
Okay. So, I mean, you can't hear anything, or you're hearing feebly? Okay. So, I think, we are okay from our end. No, audio is really long. Can you call Vivek? Okay. Okay. I think we are checking with Vivek, but you heard me when I asked you how the audio is. So you are hearing something. right? So I think I'll keep going. So this is something I did not do last time. Let's say I do this summation amortized cost, right? I'm doing this T operations totally. My goal is always there is a sequence of T different operations on my data structure. So the total cost of the amortized cost by this formula, I'm just trying to tell you why this formula makes sense and why is it justified. This is the summation actual cost plus
dt minus phi.
yeah,
potential
because there is a cancellation that's happening, so it will be phi of the final potential minus the initial potential. Okay. Now my interest is this, right? I really care about the actual total time. Amortized cost is something which I brought in to do my estimation, and so summation actual cost plus so if I ignore this, because phi is always greater than or equal to 0, so that means it's less than or equal to, and if, okay, so I can just leave it here. So if I really care about the actual cost for this sequence, then this formula makes sense, that if I just plug in amortized cost into this formula using some potential, then typically you're going to start with initial potential 0, otherwise you can compute the initial potential and add it to it, and we want an estimate for it. I gave you an estimate for summation amortized cost, right? So somehow so here the interesting challenge is, what is the potential? Who gives you this potential? How do you come up with this? And that's what makes it harder. Okay? Again, for the potential, you can intuitively view it as the amount of charge in the data structure. Right? This is the amount of charge. Which is same as the amount of overcounting I have done. Right? I'm counting the cost, and so now in the context of incrementing a binary counter, what should be the amortized cost? What is the potential? Okay, and okay, so it's all about distributing this cost carefully, right? So what we saw last time was this: when I am doing a binary increment, there are some 1-0 flips, there are some 0-1 flips. How many 0-1 flips happen?
Same as 1 0.
No, in one increment.
Oh, in one increment.
In one increment,
How many which flips?
how many 0-1 flips happen?
One.
At
One.
most one. At most.
At most.
Yeah, assuming I don't go all the way, it's exactly one.
Yes.
Right? Is that clear? How does an increment work? I start from here, change the 1 to 0, and change this 0 to 1 and stop. That's an increment. Right? These are all the carry thing. So the number of 0-1 flip is exactly 1. Okay? So the way I'm going to distribute my cost of 2, right? I'm saying the amortized cost is 2, and the reason I got that is from some of this aggregate analysis. But later I'm going to tell you that you don't know, you may not even know, you just have to come up with some magic potential that works. Okay? So the 2 cost I am given, the way I'm going to distribute it is, 1, I will pay for my 0-1 flip. Okay? Because there's exactly 1 that happens. The extra 1, I'm going to put it with this 1 to say that this is the amount of overcounting done. Okay? You lost. Okay? Now you should ask me, okay, who is going to pay for the 1-0 flips? Right? The actual cost of an increment changes a lot of ones and then changes 1-0 to 1. And all I'm saying is I am going to give you only 2 rupees, okay, to account for the total cost of this increment. And I'm going to also tell you here is a way to use the 2 rupees. When you change a 0 to 1, there is a cost of 1, use that. And the extra cost, put it under 1. Now you have to come back and say, okay, how do I pay for my 1 0 flip? So how do I pay?
Initial that I stored in
The previous increments are already paid for it, right? So whoever changed the 0 to 1 has put the cost of 1, which is sort of the overcounting they have done. So the invariant, which is the potential, is the number of 1s. So every 1 has a charge. That means every 1 has been already there is an overcounting of 1 unit that is done on those 1s. So now you use that to pay for the 1 0 flip. So cost of 2 units is enough for you, because use 1 for the 0 1 flip and 1 to put it on the 1. Okay. So what is the potential then? Which is the amount of charge in the data structure. What is the potential?
number.
Number of? Okay, from there, what is the charge? What is the potential?
Number of ones.
Number of ones, because every one has a charge, right? The invariant we have maintained is that every one has a charge. Whenever I change a 0 to 1, I pay for 1 and then put to 1. So the number of ones is the potential of the data structure. If once you come with this potential, now it's easy to compute the amortized cost. Okay, let's plug it into this formula. Amortized cost is the actual cost. I don't know the actual cost because an increment does so this is one increment. So it does some k flips. Let's say the actual cost is some k. K flips it's doing. Now, if it does k flips, what happens to the potential difference? What is the potential? The number of ones. So how does number of ones change? It decreases by, well,
Number of ones.
Wait,
Number of ones in that value.
yeah, number of ones. So the total number of flips is 1. Then this is k minus 1. These k minus 1 become 0, so it decreases by k minus 1. But then there is an extra 1, so it decreases by k minus 2. So my potential difference is this. Actual cost, because it's a decrease, I'm putting a minus, and that's equal to 2. Okay. So here is another way of arriving at the same amortized cost. One was the aggregate method, which somehow we looked at the overall thing and argued it. And the other method is some magic potential we come up with for the data structure. In this case, what that potential became obvious because of this credit thing. As we go to more complex data structures, it may not be obvious, but something you just plug it in and works in this formula, that's fine, because the way I argued it, it gives you an estimate. Okay? So in this case, this is the potential. Okay, good. So now the other example again.
So is there any other method also called accounting method where I think there is a local bank instead of a
Yeah, so this credit method is also called accounting. So instead of potential, you can argue in terms of this charge of number of ones, right? So I put a charge and
there is a local bank. Each bit has a
1.
Yeah.
Yeah.
Yeah, I mean, you
instead
can-
of a,
Yeah,
You can
each
assign
bit has
that.
a 1. So you can think in terms of that's the way I actually argued, right? Initially, before I got to the potential,
Yes.
I argued whenever you use these 2 units to pay for 1 flip and put a charge on that 1 unit. So that's some sort of an account. Okay.
So I mean, you can put the credit to the either to the data structure or to the objects.
Exactly.
each object has.
So keeping it with the object helps you, because now you know that an increment does 1 0 flips, and for every one has a charge, so you can use that to pay for the 1 0 flip. And the 0 doesn't have a charge, so use 1 unit to pay for it and maintain the invariant that every one has a charge, so use that. And this kind of, getting so well into the data structure may not be so obvious as we get on, but I just want to keep reminding you about this. So the other example again, toy example we saw was this stack operation. Where we wanted to maintain a stack to support push, pop, the standard operations, and then I also have a multi-pop. Let's use the same analogy. That means, so this is a standard push an element into the stack, pop the top element. Now I say pop the top B elements of the stack. Okay. But what if the stack does not, B is some constant, right? Fit some large number, whatever, something. Okay. But what if the stack does not even have B elements? Then you pop the whatever number of elements in the stack. So that actual time for this would be minimum of, okay. So now we want, okay, I just give you a sequence of blah blah blah, some sort of T operation, and I want to understand the time for totally how much time it will take. Again, the worst case for one of these operations is at most P. So the immediate rough estimate is T times B, and we want to give a better estimate. And we looked at both the aggregate method and potential method. So what was the aggregate method argument?
So, okay, so it says like that for a push operation, so you the cost is exactly 1, and pop also exactly 1, but for this multi-pop you have to pick the minimum of P and
Yeah, exactly. No, but we just had a, we looked at this whole thing and we had a simple observation which told us that the amortized cost is constant.
Yeah, the size, the number of elements present in the stack.
Okay, that's a potential. Okay, you're just coming high. Now, the idea is, suppose I break this up into single pop operations and every pop takes constant time. Okay, the idea is, what is the maximum number of pops, the real pops that I mean, there will be some pop operations where you go to the stack and find out that there's nothing there and you come out, right? But what is the total number of real pops possible?
Number of push
It's upper bounded by the number of pushes, right? And that's it. That is this big aggregate analysis which says that, oh, you might be spending a lot of time for these multiple pops, but if you just break open all of that and count the total time for all the pop operations, including the multi-pop, it's never more than the time for push operation. Okay, by time I mean the number of elements popped or pushed. So number of push is never more than T, because totally there are T operations. So total time for pop is also at most T, so that's 2T. Not T times B, but at most 2T. And you can come up with a potential argument, which is that every time it's like the 0 is changed to 1, you pay for it and you say, oh, somebody will change you to 0 later on, I'm going to give you a charge for that. Right? Similarly, when I push an element into the stack, I'll pay 1 unit to pay for that, and then put 1 charge on that element and say later on if somebody is popping you, use that. Right? So the amortized cost is 2, and that's all we went through last time. Okay. So now let me get started with slightly towards the end. One observation I made was that if I am doing this increment operation, right, we saw that the amortized cost of an increment operation is constant, 2. Suppose I sneak in some decrement operations also in between, right? So my sequence of operations is not, it's increment, 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 decrement, increment, decrement, decrement, and so on. Then what do you expect?
Order B.
Order B. The amortized cost will be order B, because you can come up, see, minimum time for I will also say worst case sequence. Right. So amortized complexity is for any sequence of operations, this is the upper bound. right? That's what I'm arguing here. When I say amortized complexities of an increment is 2, you do it, you start from 0, 0, 0, 0. I have to start with 0, 0, 0, 0, so that potential is 0. Otherwise, you have to add this number, whatever the potential is. You start with 0, 0, 0, 0 and keep on doing any number of increments, any sequence. I know that the amortized cost, which is the average cost over that sequence, is at most a constant, which is 2. Can I say the same thing for, you start from 0, 0, 0, 0 and do any number of increments and decrements, that the amortized cost is constant? No, because I can give you a sequence where the average cost would be B. So what would be that sequence?
Decrement, then increment, then decrement, increment.
Okay, you start off with that?
From zeros, if we decrement, we will get all ones.
Okay.
And then increment all zeros.
Yeah, so suppose I start with 0, 0, 0, 0. Let's say I do some increments and get to this. Okay, so this will be like, t by 2. So suppose I do t many operations, I do some half the operations, we get a lot of ones here. Some proportionate to b by 4 or b by 10, some number of ones here. Then I do an increment, that will cost me b. Then I do a decrement, it will cost me b. Increment will cost me. So there is no, I'm not gaining enough potential to pay for it. Every operation, only if you have some cheap operations, then you can build up potential. Right? You can sort of do over-counting to pay for an expensive operation. But whereas here, what we are observing is that it just keeps changing. If you just keep doing this, then the argument breaks down. It's not true that the amortized cost is constant. The amortized cost can be theta b. Okay. Just something to keep in mind. Okay. So the next problem we want to do is to maintain a dynamic table. Again, to start with insertions. I'll explain what that means. So you have a program or something which requires some table of some size. Now you don't want to ask too much space because you might not use all of it, so you will waste it. At the same time, you don't want to ask too little space because then immediately you will need more space. You have to ask your operating system for it, right? So you have a table of some size. Now, if there is you want to insert some element, and it tells you which location to insert, and if there is space, you will go and insert it. But if the table is full, you want to ask your operating system, not just for one entry, because you want things to be contiguous. The operating system may give you a location which is somewhere else. So what you want is you want to ask the operating system for a larger table and copy all of these elements there. Whenever you need to expand your table, your goal is to ask for a larger table and copy all of these elements appropriately and then start your insertion. Okay? So there are easy insert operations and hard insert operations which involve this table expansion. Okay? Now I don't want to waste too much space, so whenever I am going to ask extra table, I will ask for double the size. So easy insert. There exists an empty location, insert it. And hard insert. This table is full. Get a table of double the size. Insert, so copy all elements into the new table. And insert. So now our goal is that I'm doing a sequence of some t many insertions. What is the total time? Okay. The worst case could be as bad as t, because maybe rt minus 1. I had this table which is full, and then I'm expanding it and copying all elements and putting it there. So this suggests something like t square as an estimate, and we want to do a tighter estimate for it. Okay, so suppose I start the first insert, right? That cost me 1 unit of time because I start with a table of size 1, so I'm just inserting. It's an easy insert. Second insert, right? The table is full, so I ask for something of double the size. So copy it, so it costs me 2 units of time, right? So it's like this, my table is like this. Now I ask for a table of this size, copy it here, and then put my new element here. So that costs 2. Third insert, again the table is full, so I will ask for a table of size 4. Copy this there, and then I insert my new elements, right? That costs me 3. Fourth insert will be, I'm just going to put it here, it's free, right? So this is 1 unit. Okay? Let's do one more and then we'll try and see if I can get a fifth insert. Will cost me how much time?
A new table 5.
5, right? Create a new table. 6th, 7th, 8th insert would be, and the 9th insert would be
Again
9. So what is the pattern? So now what is the goal? I'm doing some t insertion and I want to know what is the total cost. Okay. So cost of ith insertion is,
It's a power of 2, if it's power of plus 1, then it will be
so it's
I.
I if I minus 1 is the power of 2 and 1 otherwise, right? So now here it's the aggregate analysis is easy because all you want to do is to add this. I actually have the actual cost for the ith insertion, which varies, but I know what it is as a function of I. Life is easy, so I just have to sum this up. What is the sum here, right? So if I'm doing this t so I can write this as 1 plus I minus 1. Okay? So this is the power of 2. So there is a 1 which is there everywhere. So this is going to be 1 plus all the powers of 2 in the i's I have, right? Because, right, think of this as 1. So there is a 1 always here and 1 here. Only if it's a power of 2 plus 1, and that power of 2 is added. So it is simply t plus summation all the powers log t, right? Because I'm doing t operations. So how much is it? So geometric series. Okay, the sum of geometric series is going to keep coming again and again, so you better understand the sum of the geometric series formula for it. And the easy formula is essentially the last term dominates it. Okay, you can just sort of, if this is a constant, then the last term dominates it and asymptotically. So more precisely, it will be log t plus 1 or 2 to the power, yeah. Right, so this is 2 to the power log p plus 1. Yeah,
It will be divided by 2. So,
2 minus 1.
2 minus, sorry.
So there is no nothing more. So this is basically 3. So which tells you the amortized cost is really 3. Okay. That now we will see some nice credit potential argument to see why it's 3. Right? Yeah. So I mean this is the aggregate analysis. I am interested in T insertion. I actually know exactly ith insertion, right? In the case of binary increment, you can sort of maybe figure out what is the cost of ith increment and compute the formula and do it. We did not do it, but that's one way to do it. But if I want to think in terms of potential, let's say, I mean, it tells you every increment should come with something like 3 credits, okay? So basically there are these easy, so suppose I have this table, okay? And
It's like one for copy, one for creating the yeah.
so what is the point?
One for
So there are
insertion.
these hard insertions which require copying this entire table.
Yes.
Somebody must pay for copying each element. So by the time the table becomes full, there must be enough credit in the table to pay for it, because I'm going to give you only 3 units for the operation, right? So that operation is not having enough money to pay for the copying the entire table, so you build it up. You build up this potential as you come, right? So we want to think about how much is the potential and what is the credit argument, right? So let's say the table got expanded. Right now this is table got expanded, so this is full, and I inserted the new element. Okay, the table got expanded, so this was basically this is full, and I have this new element. So the scenario before was that this was the table, and I want to insert a new element. There is no space, so I created a table of double the size, and then inserted the new element. Typically when this hard insertion happens, the potential will be 0, because you're paid for by all the potential, so there is nothing here. Okay. Thankfully now another hard insertion is not going to happen soon. How soon or how late will it happen? That all these guys need to fill up, right? Now when I am doing the insertion here, they are going to build up potential. Build up potential for what? To one to pay for the insertion,
Next.
and one to pay for copying this element. But what is the extra one? There are 3 units. Somehow it tells you that. So suppose I come with 2 units. Okay. Suppose each operation comes with 2 units. One to pay for that actual insertion, and one I put it as a charge here to copy this element. So now when the table gets filled, you're going to copy all of them. There is enough charge to pay for these guys. Who's going to pay for these guys? When the expansion happened, there was nothing here. At least that's sort of the invariant that's going to happen, right? So that's why you need to come with 3 credits. One to pay for your insertion, one a charge on you for your copying, and one you help somebody here. Okay, you put a charge here for 1 unit, right? So now when all these insertions happen, everybody has a charge if you actually provide 3 units of charge. Now the expansion happens, so everybody is paid, all the charges are emptied out. Now this is full, and now you are inserting all these elements. So there is no charge here. Then this whole game starts. Okay, so the 3 units idea is because you want not just to pay for your copying, you also help somebody else, because when the table expansion, when the hard insertion happens, potential is all wiped out, because that is one of the typical invariant in this potential argument, is that you build up potential for an expensive operation. So when an expensive operation happens, potential is wiped out, right? Like for example, if this is the insertion you are doing, then every one had a charge, but after this was an expensive operation, all these charges are wiped out. Okay? Only this element now has a potential. That's what's going to happen. So there is no charge here. So if you come with one extra credit, you can only pay for your insertion, but that's not good enough. So you come with 2 extra credits. So now tell me what should be the potential, right? What is the potential? And then we will do the amortized analysis of the insertion. So phi of this table T is, well, I already told you phi is basically the amount of charge in the data structure or the amount of overcounting you've done, right? How much charge is there? Suppose I have filled up table up to this point. Then how much charge will be there? Number of elements, this. Into 2, exactly, right? Number of elements up to this point into 2, right? Because 1 to pay for this insertion and 1 to pay for this. So it's 2 into, so the potential is 2 into,
Number of insertion after last extension.
yeah, or total number of elements in the table, right? This is the number of elements in the table minus size, so I am introducing 2 parameters here, minus size of the table by 2, because this is the size of the table by 2, because this is when it got expanded. So how much more I've inserted here after the expansion, which is exactly 2 into the number of elements. So this is yeah, okay. This is 2 into number of elements minus size. Somehow, I mean, even here it is not a magic. Somehow we worked our way through and figured out what the potential should be. First thing is the potential should always be 0. Okay? In our argument, which we did not use, is this always greater than or equal to 0? Sorry, not equal to 0, greater than or equal to 0. Why is it always greater than or equal to 0? Because we always ensure that the table is at least half full. Right? Table is at least half full was always that, that is one of the criteria we said we don't want to waste too much space. Right? That's how we started off. So the table is at least half full means what? That number of elements is greater than or equal to size by 2. So this is greater than or equal to 0. This is the invariant we always maintain every time when I expand it or otherwise. Good. So now let's just plug it into the formula and verify what is the amortized cost of an actual insertion. Right? So amortized cost of an easy insertion. What do you expect it to be? 3, right? That's what we told. Amortized cost always we expect everybody has to come with 3 credit is what we have estimated. Let's see. We plug it in the formula and see what happens. Well, because this is my potential now, right? So if I'm doing an easy insertion, the size of the table doesn't change because I'm not expanding or anything. So this will cancel out, right? So okay, what is the actual cost? 1. Because it's an easy insertion, space is available, I'll copy it. Plus, what is the potential difference? What is the change in the potential? Size doesn't change, so it will cancel out. Number of elements increases by 1. So 2 into number of elements increases by 2. So that's equal to 2. Okay? So this is the actual cost and this is the potential increase. And this is the potential. So potential is something of the data structure And the way we discussed, we can talk in terms of charge with the elements or charge with the data structure. Let's look at a hard insert. So this is the ith operation. It's a hard insertion. So actually no, I don't even need this. Hard insertion. Okay. Well, what is the actual cost, right? So let's use this notation: number of elements in the table and the size of the table. Okay. So what is the actual cost? Okay, maybe I insertion. Right. So I will use num I of t, the number of elements after ith insertion, and similarly size, and the before would be I minus 1. Okay. So actual cost, the potential after the ith input. So this is a formula, right? So what is the actual cost? Number of elements, right? After the ith insertion. Because every element is going to be copied. It's a hard insertion, so we have got a new table and we copied all elements, including the ith element. Now this is my potential. Let's just plug it into the formula and see what happens to the potential change. Phi of Ti is 2 into number of elements after ith insertion. Okay, I could use this, that's easier. Minus size of Ti minus 2 into Ti minus 1 minus size of Ti minus 1. So everything, size changes, number changes, let's capture all of that. So number changes by 1, right? So 2 into number of this by minus this will be a plus 2. Okay, sorry. Plus 2 because this minus this, plus, right? Because it's minus of. So this minus this is exactly 2 because the number increases by 1, so I'm just putting 2. Now let's talk about size. Size doubles, right? So size increases by double, so it's plus size of Ti minus 1, or minus of, right? So what I have is, this is what? Minus of size of Ti minus size of Ti minus 1. Right? That's what I have. Because in the minus size of Ti minus size of Ti minus 1, since size of this is double this, when I subtract it, it's exactly this size. So I have a minus there. So number of elements in, it's basically number of elements in Ti minus 1 plus 1, right? And then plus 2 minus size of Ti minus 1. And these cancel out because, why did you expand? Because the number of elements before was exactly equal to size. So it's equal.
Table was full.
The table was full, exactly. So size and number were same because so somehow this potential, putting it here by magic, I mean, we knew this by this aggregate analysis, the amortized cost is 3, but it also follows that it's 3. After I mark, sorry, before. Good, we managed to do this without any problem. Now let's just say, I suppose I also want to do deletions. Okay, so this shows that on this table insertion, actually this is something I think is really used in practice. In some operating systems actually implement this. If I would really want a contiguous set of locations without really wasting space, then every time when I want to, when the table is full, ask for double the size. Somehow this doubling, it's sometimes called doubling argument, it comes up a lot of places where it can easily show the amortized cost is constant if you do this kind of a doubling thing. Okay. Now if I also want to include deletions and still want to maintain that the table is at least half full, I can get into problems very similar to the increment decrement thing, right? Because if I always want to make sure that my table is at least half full, then I should have kept it, okay. So now to include deletion, so let me define, this is the number of elements by the size of the table. This is called the load factor. And we insert this during the insertion. Right? Just to avoid space, wastage of space, we insert this, and somehow we said that even with that kind of a constraint, some insertions are harder, but overall the amortized cost is a constant. But if I want to maintain, to include deletion, if we still want that the load factor to be greater than or equal to half, then you can get into problem. Right? You can't guarantee amortized constant cost. Why? What kind of a sequence will get you into problems?
Sequence of deletion is question.
Yeah, so suppose my table, so I built my table and it was full, let's say. It was full, and because you want to maintain at least half full, so you created double the size and inserted this new element. Now I delete this, right? Okay, deleting this, you are still greater than or equal to half. Suppose I delete 2 elements. Once I delete this, your table is becoming less than half, so you're going to contract the table, which means maybe you will just get a table of size with only 1 entry free. And then you insert, and one more insert will let you contract. So every 2 operations will give you an expensive operation. Okay? So we're going to relax this a little bit and say, okay, no, for contraction, go up to 1/4 load factor. Okay? So if the table is only half full and you're deleting it, do not contract immediately. Just go let it go down up to 1/4 and then you do your contraction. Okay? Then you expect constant amortized cost, right? Do you see why? So let me just say, so then amortized cost can be large, right? Basically omega t to do t operations, which is basically a number of elements. You may have to copy all elements all the time, pretty much, okay, some fraction of elements. But, so now, so relaxation, expand if alpha t is 1, right? Expand meaning double this space, and contract if alpha t is less than or equal to 1 by 4. And why do you expect amortized cost to be constant now? Because if I am half full, so I suppose I expanded it, I am only half full, and I delete an element, I am not going to contract it. I need to delete some fraction of elements, right? So I can make them pay for it. Pay for so since there is a large number of them, a fraction of elements are going to be deleted, charge them, overcharge them, instead of the cost is 1, charge them 3, so that later on when you want to contract, you're going to copy elements and things will be fine. Okay? So now how do we want to argue this, and what is the amortized cost, or what sort of potential we want to come up with? So it turns out the following potential works. So if the load factor is greater than or equal to half, then make sure for expansion that everybody has like 2 credits, whatever number of elements minus size by 2, right? This is the old potential, right? If I have if my load factor is more than half, so this is full, then make sure that all these elements have 2 credits attached to it. One to copy that element, and one to copy some friend of his from the top half. So when this gets filled up, everybody has a credit, you can do it, and that is exactly 2 into a number of elements minus size by 2, right? This is the old potential. If the load factor is less than half, right? So that means, let's say, only this much is full. So this is my half. Then you can think of it as maybe, how did it even happen that load factor is less than full? Some element, these many elements got deleted, right, intuitively. So make sure that these guys pay some 2 units, so that actually 1 unit. They pay 1 unit, so that when this becomes this much, that all of these guys have a credit, so that you can copy and contract. Okay. So the amount of credit now I'm going to say. So again, if this is full and this is the half point, and the reason this has happened is this many elements got deleted. Because otherwise we always maintain that load factor was greater than or equal to half as expansion. So these guys got deleted, I allowed them to get deleted because I am building up potential. So when I delete, I'm going to charge them an extra 1 credit, which I will use it for each of these elements. So when this becomes like 1/4, then everyone here has a credit. Now you can contract and copy it. So the amount of credit, if alpha t is less than half, is this number. How do I capture this number?
Size t by 2 minus number of elements.
Size t by 2 minus number. Exactly. Right? This is the size t by 2 minus this is the number of elements. Exactly. Now let's again verify that the potential is greater than or equal to 0. This we already have seen. In the load factor we always maintain greater than or equal to half. We know that number of elements is at least half the size in this case. What about here? Again, we make sure that alpha t is greater than or equal to 1/4. This is always. So that size of the table is at least 2 times the number of elements. Is that clear? Or I'll just maybe use alpha t less than half means what? My definition is number by size is less than half. So 2 into, yeah, number of elements is less than size t by 2. So this is positive. Okay. Okay. So now let's plug it into my formula and see how much time it costs for easy insertion, hard insertion, easy deletion, and hard deletion. Right. Easy deletion is that I delete an element and no contraction happens. Hard deletion is that when I delete, that table becomes 1/4, so I have to copy everything. Right. So there are 4 cases, and all of them are not okay. Let's see. So now amortize. So there are. Let's do easy insertion. Well, not just 4 cases. You also have 4 into 2, 8 cases, because you assume that before the insertion the alpha was greater and maybe it became, alpha was less and then it became increased. So because your potentials are different, so it's 4 into 2, 8 cases. Okay. So let's do alpha t suppose was greater than or equal to half, and I'm doing easy insertion. This is exactly the same as what we did before, because the load factor is always greater than or equal to half, and I'm inserting, so the actual cost will be 1. Amortized cost, only table doesn't change, the size, number of elements increases by 2, so the amortized cost is at most 3. If I do a hard insertion, again exactly similar to what we did, will be 3. Okay, this is old analysis. Deletion will be even easier here because alpha t is greater than or equal to half. It's only easy easy deletion. There is no, because one deletion will not bring it down to 1/4. So easy deletion is the number of elements decreases by, okay. So my potential is still here, right? So I'm doing this. So when I'm doing deletion, the actual cost, I'm deleting one element. And the potential size doesn't change. This is the potential because alpha remains greater than or equal to half. Okay, alpha may become less than half. So maybe after the deletion, alpha may become less than half. So I need to argue carefully. So let's do this. Okay. So let's get to deletion. Or even insertion in the case when alpha is less than half, right? Let's finish insertion first. So I did this easy insertion, hard insertion, assuming this. Let's do easy insertion, hard insertion if alpha t is. If alpha, I have to be careful here, alpha ti is less than half, and alpha ti minus 1 is less than half. Right, the table was less than half full and I'm inserting an element. It should be the easiest case, right? And you'll see that it potentially will actually, the amortized cost will be even negative. So I am in a situation where less than half full, I am inserting it, it's still less than half full. Okay? Remember, I do allow less than half full, I am allowing up to quarter full, right? That's the load factor we are allowing up to quarter full. So if this happens, then the amortized cost is the actual cost plus the potential minus. What is the actual cost? Is 1. You can say easy insertion. There's nothing, no table expansion, nothing is happening. And what happens to the potential? Now you are in this zone. Potential is, the size cancels out because there is no change in the size. Size of the table doesn't change, so it cancels out. Now number of elements increases by 1, but you are decreasing the number of elements, so it will decrease by 1. Right? It will be minus number of Ti plus number of elements in Ti minus 1. Now since the number of elements is 1 more than this, so it will be 0. The other case, if insertion alpha Ti becomes equal to half, now you have to be careful because your potential changes. Okay, but you expect all this to work out fine, but let's just work it out. Okay, I'm not going to work all possible cases, we'll do something. So if this happens, then again there is no change in the size, but the potential changes, so let's work it out. So the amortized cost equal to actual cost, which is a simple insertion because no table change, nothing happens, plus phi of Ti minus phi of Ti. Okay. Well, what is a new potential? Because alpha I becomes half, so I am into this domain. 2 into number of elements in Ti minus the earlier potential was size of Ti minus 1 by 2 plus number of elements in Ti. And you expect everything to cancel out and become a constant. Let's see whether that's happening. Right? Size was all, size of the table doesn't change, so this is 1 plus number of elements increases by 1, so I'm going to write this as 3 okay, plus 3n of Ti minus 1 minus 3s of Ti minus 1 by 2. You agree? Yep. Because n of Ti is 1 more than n of Ti minus 1, so that 1 I took it out and I added it here. So it's n of Ti minus 1, how many of them? 3 times. And this is s of Ti minus 1 by 2. Okay. Alpha Ti is exactly half. Okay, I wish I had used Ti. Okay. Yeah, let's get to Ti because then I want to use this fact that there is a size and the number of elements relationship on the Ti. So let's just go back to Ti, which is n of Ti minus 1. So this is 3 times n of Ti. That's good, right? Because n of Ti is 1 more than n of Ti minus 1. So this 3 accounts for it. Minus 3 s of Ti by 2 because the table size for concerned it's the same. Now that cancels out, right? Because n of Ti is exactly size of T by 2. So this is 0. As alpha Ti is equal to half, which is equal to, by definition, so when in the less than or equal to half domain, when I am trying to insert, the amortized cost is really nothing. Okay, and in the greater than or equal to 2, it's little more analysis, but it's still again at most 3. Okay. So now let's just do deletion. I'll do one case and then we will stop because it's just more calculations. Let's do the hard deletion, easy deletion, and then so let alpha t and minus 1 be less than half. Now I'm doing a deletion. I also have to do the other case, which I'm not going to do. Okay? So we're doing an easy deletion. Since I erased the potential center, let's write down somewhere the definition. So phi of t is if alpha is greater than or equal to half. Tell me what it is.
2 n t
2 into n of t minus
size
of t. And in the other case,
of t by 2.
size of t by 2
Minus
minus
one.
n. Right? So since alpha is less than half, I am in this potential domain. So easy deletion is that my table is less than half full because alpha is less than half, but it does not come down to 1/4, so I just delete an element. So the actual cost is 1. Let's see the potential. The size doesn't change, so that cancels out, and the number decreases by 1. So it will be minus n of ti plus n of ti minus 1. So this is 2, right? Let's do an amortized cost of hard deletion. Well, when does that happen? Because the table has become 1/4 full, so I am copying all elements, creating a new table and copying it. So what is the actual cost? The actual cost is after the deletion, whatever number of elements are there, I have to copy them. And I also have to charge 1 for the deletion. Right? One element got deleted, there is a cost of 1. And then there are so many elements left which I have to create a new table and copy it. So this is the actual cost. Now potential, we just have to plug it in and we get it, right? What is the potential? I'm in this domain. So the number of elements decreases by 1, but it is in the minus domain, so it will be a plus 1, right? Change in n of t. Now let's look at the size. What happens to the size, right? So this is plus size of ti by 2 minus size of ti minus 1 by 2. So what do I do when I contract? When the table becomes 1/4, right? Only this much is there. Then I just give away this half of the portion because I want to make sure the load factor is at least half, right? So I will copy and put this. So the table size becomes half of what it was. Okay? So this would be n of ti plus 2 plus, so the new table size is half of the original table size. So I have to write this. This is basically size of ti minus 1 by 4. So minus size of t of I minus 1 by 4. Right, because this I would write it as size of ti minus 1 by 2, so size of ti minus 1 by 4. This is a plus, but this is minus half plus 1/4, so it will be minus 1/4. Size of ti minus 1. That's it. So now we should be done, right? What do we know about number of elements after this? Well,
This was already.
it's 3 plus, so n of ti minus 1 minus size of ti minus 1 by 4. And these two are same. That before this deletion, or maybe actually it's after that deletion. Yeah. So when I deleted this element, it becomes, so these two are the same. Okay. Right. So I don't need to do the 3 plus. When I deleted this element, now it has become 1/4, which I allow. No. So after I delete, it becomes less than 1/4, which is what I don't allow. So that means before deletion, so okay. So it's 3, it's 3. Okay. It's 1 plus n of ti minus 1, whatever the number of elements before. Whatever the number of elements before was exactly 1/4 of it. With this deletion, it became strictly less, and that's why I went for contraction. So it's, but the important thing is you can see these big numbers cancelling out. That's the power of this potential. Right? So whenever there is a huge cost involved, there is enough potential which cancels out. Okay, this is what we saw in the multi-pop stack, or when increment cost was very high, whenever it was changing once, there was a huge potential because everyone had a potential and that cancelled out. Okay? So you will never see some non-constant quantity coming up here. So the other case which I did not do is that if the load factor is greater than or equal to half, you are doing deletion. And when you do deletion, the load factor may remain greater than or equal to half, or it may come down to equal to half. But essentially, you know the actual cost. Actual cost is simple because in the greater than or equal to half, when you delete, actual cost is only 1, and the table size doesn't change. So you just have to, the potential may change, you have to plug it into the formula and verify that it remains at most constant. Okay, so these are all building up potential to practice amortized complexity. Okay, so now I think I will, stop here. Next time we will actually get on to some variation of heaps where we will focus on the amortized cost. In the standard heap, you can do insert and delete min, or insert and delete max in logarithmic worst case time. But we will come up with some variations where actually you can do insertion in constant amortized time and things like that. Okay.